According to Wikipedia, a computer is a digital electronic machine that can be programmed to carry out sequences of arithmetic or logical operations automatically. The keywords in this definition are machine, electronic, digital, and programmable. In a generic way, any machine or mechanism that meets these conditions can be called a computer. Even so, we can extend the definition considering that a computer has a processor that is in charge of carrying out a series of operations previously planned in a program, for which you need some data inputs and some outputs to represent the results from the input data. In the common practice that we all know from personal computers, the mouse, keyboard, and camera would be on the input side, while the screen, speakers, and printer would be on the output side. Programs and their data are stored on storage devices such as hard drives or physical memory. Hello and welcome to the Computer Architecture channel for Electricians. My name is Johan Huuk. I am a retired industrial engineer, and I have worked for a large part of my life in the field of industrial automation, process control software, and smartphone apps. In a video series starting today, I'm going to explore how computers work internally, also including some forays into history. I'll start with the basics and work my way up to relatively advanced concepts. I am going to build from scratch a computer capable of executing tasks such as arithmetic operations and small mathematical algorithms. The idea is that anyone with a general knowledge of electricity will be able to follow and understand the process without any difficulty. The original spoken content will be in Spanish, but in order to facilitate a possible dubbing into English in the future, the texts that appear in the videos will be written in this language. I'll also try to spend enough time adding English subtitles on the original footage. To honor the title of the series, I have decided to use only electrical switches, that is, the electromechanical relays that we all know. However, for practical reasons, especially reliability and size, I am going to build the final design with solid-state relays. The project is quite ambitious in the sense that I am not going to limit myself to a minimalist version of a processor, but I am going to apply current knowledge in the field of computer architecture to create a relay computer that will potentially be the fastest that has ever existed. Or at least that will be my goal. One of the most impressive historical examples of an electromechanical computer was the Harvard Mark I, which was built in 1944 and was used, among other applications, for the calculations of the Manhattan Project, which led to the development of a first atomic bomb. Mark I was decommissioned in 1959 when it fell out of use and is currently only partially visible. Interestingly, the same year the Facom 128 was put into operation in Japan, an extremely reliable computer for the time, which is still kept in perfect working order at the Fujitsu headquarters. Currently, there are numerous examples of computers that fit the definition we gave above. The best known are the personal computer, the digital tablet, the supercomputing center, the digital microcontroller, the industrial PLC, and even the programmable calculator. That a computer is an electronic machine ultimately means that information is represented by electrical signals, usually voltages. At its core, a computer is made up of a series of circuits that transfer electrical voltage levels, and everything that happens inside it is represented by electrical levels. The vinyl record player is obviously not a computer, but it also makes use of electricity as a transmitter of information. The music is stored on the disc as grooves, with a geometry in the form of undulations that are analogous to the sound waves of the music that is recorded on them. When the player's needle travels through the grooves at the proper speed, its vibrations are converted directly into an electrical signal, which is then amplified to reproduce the sound. All this occurs thanks to the processing, in this case, of analog electrical signals. In the case of the classic CD player, the general principle is surprisingly similar except for one important detail. Instead of starting from an analogy of the sound waves stored on the disc, what we have is a numerical, that is to say, a digital representation of the waves themselves. At the time of recording, the sound wave is split or divided into sufficiently small intervals. The numerical values of the amplitude of the wave that we obtain in each small interval are sequentially printed on the disc. During playback, the read head interprets the sequence of numbers that is recorded on the disc and converts it into digital electrical signals representing those numbers. Finally, the audio is recomposed from the initial numerical sequence. As simple, at least conceptually, as this process may seem today, it is curious to mention that prior to 1960, and despite the existence of relatively advanced digital technology at the time, it was not believed possible that audio could be represented digitally. Engineers at the Sony company in Japan were the first to prove otherwise, and a few decades later the same company was one of the pioneers in the commercial development of digital music. Although the process of playing a CD is completely digital, the CD player is obviously not a computer because it lacks one very important feature: being programmable. This is what really differentiates a simple digital device from what is considered a computer. A computer is not only capable of carrying out specific tasks, but can be programmed to alter its functionality in a highly flexible manner. However, that a device is programmable does not necessarily imply that it is digital, or even that it is electronic. For example, the Tide Predicting Machine on display at the National Oceanic and Atmospheric Administration Museum used a series of pulleys and other non-digital mechanical elements that could be configured to predict tides anywhere in the world. Similarly, the fact that a device is digital does not necessarily imply that it is electronic. For example, the mechanical calculators that were used before the development of digital electronics were completely driven by mechanical mechanisms and levers. The abacus, an obviously digital tool, was used in China to facilitate mathematical calculations long before the invention of electricity. But not even all computers were digital. Before the great development of digital computers, and until they offered the necessary features for certain functions, programmable analog machines coexisted, which used electrical signals for complex simulation applications, and which cannot be called true computers, as they lacked one of the defining characteristics. Remarkably, the forerunner of digital programmable machines, as we know them today, was not even electronic, but mechanical. The Z1 mechanical computer built by Konrad Zuse in 1936 was capable of executing quite complex mathematical calculation algorithms, following programs that were stored on punched tape. Unfortunately, the original machine was destroyed during the Second World War, but in 1989 the inventor himself built a replica that is currently exhibited at the Berlin Technical Museum. Today, the simplest example we have of a computer that meets all the requirements and that we can find for less than €5 or dollars is this. It is an electronic board compatible with the Arduino system that contains a processor connected to some input and output ports or pins, and it is obviously programmable. In the following video, I will explore the characteristics that make digital electronic devices unique to the point that they drive everything analog to obsolescence. I will also introduce some basic concepts that will be useful for the continuation of the project. Thank you for your attention. Do not forget to add comments and make suggestions or questions about any detail that may interest you. Subscribe to the channel to get notifications of the publication of new videos. See you soon in the next chapter.